The history of math is our intellectual foundation to understanding science. Science. Beautiful, awesome, wonderful science. It's the creative foundation to our ineffable future. Hi, I'm Gabrielle Burchak, and this is my podcast, Math, Science, History. I often promote my website, mathsciencehistory.com. Of all the hosts that I've been with, my experience with Bluehost has been the best. What I really like about Bluehost is their customer service. It is top-notch. You can access Bluehost through my affiliate link, www.bluehost.com/track/mathsciencehistory, all one word. It's only $3.95 a month if you sign up for 36 months. So if you do the math, it's $142 to start. And for me, it was the smartest business investment I've ever made. There are two kinds of boyfriends or girlfriends in the world. One is the kind that are real, the kind of boyfriend or girlfriend that you date, call, hang out with. And the other kind are those that you imagine that you have. Take me, for instance. If you listen to episode 6, where I talk about my celebrity crush, you'd know that my imaginary boyfriend is Bruce Willis. And he's the best imaginary boyfriend ever. We don't argue. He takes me imaginary dancing. He watches movies with me. Actually, my dog watches movies with me, and his name is Wesley Crusher. And he actually doesn't really watch the movie. He just barks at imaginary people that he thinks are outside. But you may be wondering what this has to do with math. Well, in the world, there are two kinds of numbers, real numbers and imaginary numbers. Real numbers are those numbers that can be found on a number line. Imaginary numbers are those numbers that can't be found on a number line. So how did imaginary numbers come along, and where did they come from? Imaginary numbers weren't always the structure of the square root of -1. This concept of imaginary numbers comes from the idea that if a number couldn't be imagined in the area that it was being used, then it's a number that must be imagined. The negative number was a hard concept for early mathematicians to wrap their brains around, at least as far as we know. As far back as 10,000 BCE, negative values were used as subtrahends. A subtrahend is a number that is to be subtracted from another number. For example, 10 minus 5 equals 5. In that sentence, the subtrahend is -5 or -5. This concept of using subtrahends was commonly used and can be found in China, where positive coefficients were indicated by red computing rods and negative coefficients were indicated by black computing rods. This is also indicated in the great mathematical work called The 9 Chapters on Mathematical Art. Actually, it's called Qiu Cheng Suanshu. The 9 Chapters on Mathematical Art was a composition of mathematical works from several generations of Chinese scholars from the 10th to the 2nd century BCE, with its most recent addition to the book coming from 200 BCE. But even then, the negative number wasn't really a thing. It was just a subtrahend. It was a mathematical abstraction that could be changed to a positive number simply because a negative value wouldn't work. Such was the case with Heron of Alexandria in 50 CE. In the 1st century, Heron of Alexandria wrote Stereometria. It's in this work that we find the very first depiction of a square root of a negative number, where Heron presents a frustum of a pyramid with a square base. A frustum is a portion of a solid that is cut off by parallel lines. So in Heron's case, it was basically the foundation to the pyramid with a square base. So imagine a square pyramid and just the top part cut off. That bottom part is the frustum. In this particular pyramid, the dimensions of the bottom part of the base had the length of 28. The sides of the upper part of the base had a length of 4. And then the edge of the frustum, meaning the angled line that runs from the bottom of the base to the upper part of the base, was 15. In this particular problem, Heron needed to find the height of the frustum. Well, ultimately, when he did the math, he ended up getting a value to the square root of -63. However, the value is ultimately recorded as the square root of 63. The negative value was missing. Whether this was just a mistake by the copyist or whether this was Heron not sure what to do with the square root of a negative number, this is our first indication of an imaginary number. However, nothing was done with this. Likewise, in the 3rd century, about 150 years after Heron, Diophantus did exactly the same thing in his work Arithmetica. In 2 separate instances, Diophantus's mathematics resulted in an answer that was the square root of a negative number. However, unlike Heron, he didn't switch it to a positive number. He just simply referred to his result as absurd. Mathematicians moved forward with a positive value, and so this imaginary number would lie dormant in the world of mathematics for many more years. A really good book that talks about this is a book actually I just bought. It is called An Imaginary Tale, The Story of the Square Root of -1 by Paul J. Nahin. And it's an older book, but I'm really excited to read it, and I recommend you check it out. And so a square root of a negative number remained absurd for hundreds and hundreds of years. Then, in 1535, Niccolò Fontana Tartaglia entered and won a mathematics competition where he presented an algebraic formula for solving cubic equations. In other words, he solved x to the power of 3. As a side note, this was a time when math competitions were a big thing, and when Tartaglia entered the competition, he turned his solution into the form of a poem so that no one could steal it. However, Girolamo Cardano got hold of the solution, as did Cardano's student Lodovico Ferrari. Ferrari discovered that Tartaglia's solution could also be used for solving quartic equations. In other words, solving equations with x to the power of 4. But this was a time when math was a cut-throat vocation. Could you imagine? Cardano, after promising Tartaglia that he wouldn't publish his solution, published Tartaglia's solution, along with Ferrari's work in his own book, Ars Magna. My point of the story is to point out how these 3 mathematicians demonstrated how complex numbers could be used with combinations of real numbers in the form of a plus bi, where I represented the square root of -1. However, this value was still a head-scratcher. Enter Raphael Babelli. In my last podcast, I briefly touched on Babelli and explained his work with the square root of 13. Well, in 1560, Babelli proposed the idea of imaginary numbers. In other words, he wanted to show that imaginary numbers had useful properties, especially when solving cubic and quartic equations. The reason why is that when you graph a cubic operation, it crosses the x-axis. In other words, there's a solution because x equals something in that graph. Basically, what Babelli proposed was that if the solution is the square root of a negative number, then that is the solution. In other words, he said, let's make the square root of -1 a thing. The reason why he proposed this is because the square root of -1 behaves like a real number. For example, imagine that you have an equation that reads 7 plus 2i times I. When you multiply I times I, or when you multiply the square root of -1 times the square root of -1, you get -1. Well, -1 times 2 is -2, and 7 plus -2 is 5. So basically the answer of 7 plus 2 square root of -1 times the square root of -1 equals 5. So, because the square root of -1 can be treated like a real number, Babelli simply proposed that we make the square root of -1 a thing. And so, we did make it a thing. However, back then they simply called it the square root of a negative number. It wasn't until 1637 that the term imaginary number was coined. René Descartes, in his work La Géométrie, wrote that in a solution that, quote, the true roots as well as the false roots are not always real, but sometimes only imaginary quantities. Hence, the term imaginary was born. Thus, just like Bruce Willis in his 1987 breakout movie Blind Date, which I've seen more than the cube root of 216, the representation of I as the square root of -1 had become a superstar. Using Babelli's proposition that we just let the square root of a negative value be, and then work with it, and then call it an imaginary number as referenced by René Descartes, we now had a known value as I that we could use in our algebra. So what use does the square root of a -1 have for us today? And how can we possibly use an imaginary number? Well, Complex numbers can represent vectors. Though a vector is a line, it is represented by magnitude and direction in a complex plane. These vectors are useful in electrical engineering, physics, meteorology, and any industry that needs to calculate periodic motions. The square root of -1 can be useful in calculating alternating currents in an AC circuit. In physics and quantum mechanics, the square root of -1 resides within Schrödinger's wave equation, a wonderful linear partial differential equation that predicts the behavior of a dynamic system. In Newtonian physics, I is used to mathematically understand the movement of a pendulum. In meteorology, since I can be used to determine magnitude and direction, this beautiful complex number can be used to determine the speed and direction of wind, which for pilots is a life-saving tool. That's not to say that my imaginary boyfriend has saved lives, because he has. There was that time in Die Hard, and then in Die Hard 2, and then in Die Hard with a Vengeance, and then in Live Free or Die Hard, and then in A Good Day to Die Hard. And what's cool is that my imaginary boyfriend has a place among the real numbers too. Like that time in The First Deadly Sin, The First Kill, 4 Rooms, The Fifth Element, The Sixth Sense, The Whole 9 Yards, The Whole 10 Yards, 10 Minutes Gone, Ocean's 12, 12 Monkeys, 16 Blocks, Catch 44. Oh, and that time on The 70s Show. If you are interested in reading more about the history of math and science, please come visit me at mathsciencehistory.com. And while you are there, if you like what you're listening to, please feel free to click on that coffee button and buy me a cup of coffee. Thank you very much for listening to Math Science History. The podcast will be moving to monthly podcasts at the start of every month, so be sure to subscribe. And until next time, yippee-ki-yay and carpe diem.